pi 3 of g acting on x, y, z naught is just equal to z naught, right? I mean, technically, I guess it's the set containing z naught, if you like. But anyway, pi 3 is constant on each orbit. And what else? He says, since pi 3 is constant on each orbit, it defines a map. So, define f, he calls it f3 from S2 mod g to minus 1, 1, according to what? Well, such that the diagram S2, we got pi down here to S2 mod g, F3 is here, pi 3 is here, and minus 1, 1 is over here. He says, define F3 such that this diagram commutes. And then he makes some claims. He says F3 is obviously bijective, and then we can use the usual suspects to argue it's a homeomorphism. Let's see if we can, let's try to think through that, yeah? So this pi is what? That's the natural map of the quotient topology. So this is by construction what? Continuous, right? I mean, pi 3 is also continuous, right? How do we know F3 is continuous? What is? It's in the theorem? They said, what is a continuous? But I do think this goes back to one of the theorems that was stated even in Gamelin, right? Okay, so what is F3 specifically, or in terms of pi? And I mean, can you tell me? How does it go? F3 composed with pi equals to pi 3. So because F3 composed with the natural projection map for the quotient topology is equal to another map which is continuous, then that theorem says that F3 is continuous. Is that right? I'm asking, I mean. I guess this is theorem 13.3, right? F be a continuous function from topological space X to Y, tilde an equivalence relation on X such that F is constant on each equivalence class. Then there exists a continuous function G on X mod tilde to Y such that F is G composed of pi. I think it's 13.3 that we're using because we verified that F in this case is pi 3 is constant on each equivalence class, which here is the orbit. So theorem 13.3 in Gamelin, among other things. But he says more. Okay, great. It's clear that it's pi 3 is surjective, right? This is clear. Because I want F3 to be a homeomorphism, right? So if pi 3 is onto, that means that F3 is onto as well, doesn't it? Given that. So we have, it's a surjection, it's a continuous surjection. Okay, great. What's that? The kernel of pi 3. So you can see that it's injective. All right. So why does it have a continuous inverse? Because that's what we need for homeomorphism, right? It's not enough that it's a continuous bijection. We also need to know that the inverse map is also continuous. Why is the inverse map continuous? Hausdorff. I mean, this is Hausdorff. It's that pesky theorem 6.7 again, I think. This is compact. Quotient of compact is compact. So we're going from compact with a Hausdorff image. So I believe theorem 6.7 told us what? One-to-one and continuous means homeomorphism. FB, continuous function from compact space X to a Hausdorff space Y. If F is one-to-one, then F is a homeomorphism of X and the range. And since the range here is all of minus 1 to 1, we have homeomorphism. All right, so again, like I said, it's the usual suspects. That theorem 6.7, it's everywhere. All right, so anyway. I like this example because I can actually kind of see it. The stuff we were doing with Grassmann manifolds, it just kind of blows my mind. But it's important, you know, in terms of how these things are applied and used, because they allow us to extend past just, you know, geometric intuition, way past. He then talks about the stabilizer and, you know, he does some other things. I think I'm just going to talk just about one thing in his next section. I mean, if you read the next about 5 pages, he discusses how to do various things, such as like glue, how you can glue like a sphere onto a topological space, like just glue a sphere onto it, or glue a handle, or take 2 spaces and like puncture a point and sew them together, in terms of like forming disjoint unions and then forming an equivalence class to identify the points. It's not far from where we are to make these things rigorous. All right, so there are precise ways of making new topological spaces by gluing them together. And the way we glue things, I think, roughly speaking, is form a disjoint union and then use some sort of equivalence on the disjoint union to meld them together, roughly speaking. He's more precise here. As you read this, I also don't understand what he has to say about wedge and smash products. What he's written here is not enough to make sense of it. So if you don't understand it when you read it, you have me as company. And the same goes for his example 3 about a cone. And generally page 42, I don't understand. Because this is a snapshot of a couple dozen pages in a deeper book, okay? You got to understand this book for what it is, which is fantastic. But one thing that is worth talking about for a second before I go on here is a cone. He gives us a specific construction of what does it mean to have what's a cone. So here's his example. Cone over a set. And here's what he does. X, a topological space. He says the cone over X is by definition, what's he do? He takes X, he takes the Cartesian product of that, with 0 to 1, and then he quotients by X crossed with 1. And here's his picture for it. that make any sense? Oh, by the way, at this point in the book, he's now gone back to what we started with, which was to say that the idea of the quotient is to form an equivalence class where we're like identifying points in a certain subset of the space, like gluing them together. So at this point in Yannick, he's gone back to our starting point in the whole discussion 2 classes ago. All right. So like that's the idea, is this anything in here is viewed as equivalent. So that's saying that, and in this picture, this top, let me use some coloring here. The top right there is x cross 1, right? And so in the quotient space where we take that and smush it to one point, that point is represented over here in the picture by that. So that's the idea of a cone over a set.
So it's just taking a plane and picking a line at the top and squishing it together.
Yes.
Because the rest of the lines don't actually have to be changed based on that squishing, correct?
Right, but the squishing does affect the topology near the squishing. Like, what's an open set in the cone, right? It could, fine, it could be whatever, right? Because that'll track back over to here to whatever, right? And so this is open only if what? If the inverse image under the pi map is open. So, what's an open set up there? Ah, so you're like, yeah, maybe that's a good point to make. Is if it was something like this, right? Would that be? I don't have a good sense of what's the inverse image of something like that look like over here. If it was something that was not open over in the product topology of 0, 1, and x, then that would mean it's not an open set over there. But something like, one possible, just to give you a picture again, something like that, which would correspond to maybe something like all of this, right? And maybe that's, I don't know, maybe that's something like 0.7 to 1 Cartesian product with x, right? Other way around. And since that's an open set in 0 to 1, right? With the relative topology, we allow 1 can be included, yeah? And so that by definition is open in the product. So that means things like this are open in the cone. At least things like that are open in the cone. Anyway, but this is a way we can, but the thing that blows your mind is like this x doesn't have to be a line. This is a heuristic picture. X could be the matrix group. We could build a cone over the general linear group of n squared dimensional matrices. X could actually be a circle, so we have an honest to goodness cone. That's a more productive comment. Thank you. Anyway, I think this is an interesting construction. Anyway, it's something it's a new topological space we can create from a given one. There's also something called the suspension. If you build like another cone below, you make a double cone, it's called the suspension. That's his next example. But I wanted to spend the last couple minutes saying more about real projective space more concretely, because I think it's worth a try, because it's a good example of whatchamacallit, quotient topology. And it's also a good example of a genuinely abstract manifold, which is at the same time not that hard to work with. So it's kind of an important example, real projective space or complex projective space. It's very nicely written in this book, so maybe I'll make you a copy of these 2 pages for like when we meet again. I'll give it back to you, okay? I just wanted to write down a couple things he writes down because I think it's worth talking about. So here it is. Definition. And I think this will be a little bit less ethereal than the Grassmannian definition I gave you earlier, okay? So here it is. Pn R is equal to R n plus 1 without 0, quotient dilations. In other words, here by dilations, I mean that x is equivalent to y if and only if x is equal to lambda y for some lambda in some non-zero lambda. So this is just a fancy way of saying that the equivalence classes are what? They're just lines through the origin, right? Well, what's that? What did you say? Yeah, oh, but this says that they're lines. Yeah. I mean, that says that they're on the same line. That means x is a scalar multiple of y. So he says there's a natural one-to-one correspondence between P and R and the set of one-dimensional vector spaces of Rn plus 1 through the origin. He says, given x0, x1, xn in Rn plus 1 with 0 removed, the equivalence class in PNR is typically written we just put x0, x1 like that. And he says we put on PNR the quotient topology, which hopefully makes sense to us now, right? We give it the quotient topology. And he says that then the projection, so the projection of x0, x1, xn is equal to that equivalence class, right? I suppose, stupid zero. I mean, I'd like to say it's just the span of x. I mean, I could almost write that pi of x is the span of x, you know? I could almost write that. but span's got 0 in it, so it's kind of like I mean, so maybe you could do a, I don't know. How do you take 0 out of the span? Oh, I know. Divide by 0. There. Sorry, no one uses that notation. But it occurred to me it would be annoying if you did. Anyway, he says, composing the inclusion, ooh, this is interesting. If we look at the inclusion of Sn plus 1, oh, excuse me, just Sn, and Rn plus 1, without 0. Let me just draw the diagram here. Start Sn, include that into Rn plus 1 with the origin deleted, okay? Then you can take this R map to Sn again. And from Sn, there's a pi prime map to Sn mod tilde. There's an F map to Pn R. There's a pi map from there to there. There's F inverse, what do you know? Over here to Sn mod tilde. And then there's pi prime over here again. He claims that F is a homeomorphism and that pi produces a continuous onto map that factorizes through the continuous bijection Sn mod tilde to PNR. Ooh, I don't think I'll have time to do this justice today. Anyway, we'll keep talking about this. Hopefully next class I'll wrap this up in about 20 minutes or so. But basically, there's this like nice interplay between real projective space and identifying antipodal points on spheres, and all of this is woven together with the concept of quotient topology. All right, so I'm going to copy the pages so you can look on with me before we have this conversation next time. But so you can turn it off. So